Lesson 2.8. We're going to break this up into two parts. So the first part is going to be literal equations. The second part is going to be dimensional analysis. So we're going to focus here on literal equations. And with literal equations, what you're doing here is you're solving for a specific variable. So for example, the first problem that we have here, for example 1, we have mx plus 4y equals 3t, and it's telling us that we need to solve for x. So what we're gonna do is, even though it looks kind of goofy because you have all of these variables that are within that equation, we literally are gonna do the exact same steps that we would normally do to solve an equation, but we're gonna just solve for that specific variable. So since I need to solve for x, what I'm gonna do is I'm just gonna write the problem over on the side here, just so I have a little bit more room. So since I'm solving for x, all I need to do is I need to work on just getting x all by itself. So because this term has the x value in it, I'm gonna go ahead and subtract 4y. So then I'm left with mx equals 3t minus 4y. And since I'm solving for x, I'm going to divide both sides by m. And I end up getting that x equals 3t minus 4y over m. That would be my final answer. Okay, let's look at 1a, and we'll do 1a and then probably do one other problem from here. So 1a, same idea. This time though, I'm going to solve for n. Okay, so I'm gonna first get the term with n all by itself. So now I'm left with 15 minus 6p equals 3n. I'm gonna divide both sides by 3 so that I can get n by itself. So now I'm left with n equals 15 minus 6p over 3. And what we need to also make sure that we double check is that answer in simplest form? If you have, in this case, we have 3 different terms. If we can simplify all 3 of them, we should, okay? If we looked at the first example here, we're really just looking at the coefficients and the constants. So we have 3, 4, 1. They all can't be simplified, so that would be my final answer. So in here, I would just go ahead and divide 15 and negative 6 divided by 3 because I can simplify those out. So then my final answer is going to be 5 minus 2p. All right. The next problem that we'll do is we will go ahead and just do 1b. So for this one, we're just solving for t. Now I know your instinct is gonna say, all right, I need to distribute t all the way through. But then when you do that, you're doing more work than necessary. Notice how on the right-hand side with t, you're multiplying it by the expression r plus 4. So to get t by itself, since those are 2 terms that you're multiplying together, we just simply need to divide by r plus 4. So my final answer is t equals 28 over r plus 4. Okay. The next part of this lesson is talking about, once again, solving for a specific variable, but you might now have the variable on both sides. So in order to do that, you have to still make sure that everything that has a variable, the similar variable is on one side, everything else should be on the other. So for this one, 3x minus 2y equals xz plus 5, we're solving for x, okay? I just need to move things around so that every term that has x is on one side, every term that does not have x is on the other. So for this one, I'm gonna go ahead and subtract xz from both sides. So then I'm left with 3x minus xz minus 2y equals 5, okay? The next thing that I'm gonna do is I'm gonna add 2y to both sides because that term does not have an x with it. So I have 3x minus xz equals 5 plus 2y. From here, what you should notice is that you have an x in both terms. So this is actually going to be very similar to the problem that we did in the previous example. So when you see problems like this and you're trying to solve for x, you need to pull out a GCF, greatest common factor, which in this case should always be, if you do it right, should always be the variable that you're solving for. So if we notice in both of these terms, x is what is in common. So if I take x out, I would be left with 3 minus z. So it's almost like you're doing opposite of the distributive property. And we'll set that equal to 2y. And since we're solving for x, we're going to divide everything by 3 minus c. Our final answer is that x equals 5 plus 2y over 3 minus z. Okay. All right. Go to the next page. You have a few example problems that you could go through yourself just to get more practice. One thing that I forgot to mention, okay, is eventually what's going to happen is we're going to have to try to figure out values that would potentially make your denominator be 0. And when that happens, those are something called excluded values, okay? So if we're thinking about here, all right, and we're just gonna practice these for now, especially because that's something we will see in the future, we have to think about what value of z would make the denominator 0. Because remember, if you have in a fraction something divided by 0, your answer is going to be undefined, which is something that we cannot happen. So we want to make sure that we specify, in this case, that z cannot equal 3. Because if I plug 3 in here, right, it's going to be 0, which means that this would be an undefined equation or solution. All right, so you would do like the same thing with those practice problems. So an equation that involves several variables is called a formula or a literal equation. So that's kind of what you're doing here. So we're going to practice just a real world problem. So it says use the information about the largest yo-yo on the left. The formula for circumference of a circle is 2 pi r, excuse me. I was going to do a different formula of area of a circle. I saw that we're doing circumference, so ignore what I just said. So circumference is 2 pi r. C stands for circumference, r stands for your radius. So we're first going to take this equation, okay, C equals 2 pi r. And the first thing that we need to do is we're going to solve the formula for r. So we notice that 2 pi r, when they're next to each other, that all means multiplication. So in one step, I can divide both sides by 2 pi, and then I would be left with c over 2 pi equals r. Now that I have that equation, now I'm going to go ahead and do part B, find the radius of the yo-yo. So since we're solving for r, we are told in the information provided that the circumference is 32 7/10. So we're going to go ahead and plug in 32 7/10, and we're going to divide that by 2 pi. If you want to go ahead and represent 2 pi as 3.14, that is fine. Just know that with pi, the more decimals that you use, the more accurate your answer is going to be. So for time's sake, we're just going to do 3.4. You can also do 2 pi in your calculator, and it will give you a more accurate answer as well. So 32.7, and I'm just doing 2 times 3.14, so I get 6.28. And then if I divide those out, I get that the radius equals about 5.2 feet. Okay, in this problem, it doesn't tell you what to round to. So rule of thumb, I would just round to the nearest hundredths. If not, then to the nearest tenths like we did in this example. Okay. Here's some more examples of working with literal equations and formulas. We'll go ahead and do, we'll do 3A just to practice, and then you have 2 more problems at the bottom that you can work with as well. So for this one, we're talking about the speed, or in this case, velocity. And our formula that we use for velocity is 2 pi over t times r. Okay, so for this one, what we're gonna do is, oops, sorry. This should actually 2 pi r over t. Okay, same problem, just making it a little simpler for us. So r is the radius, t is the time that it takes a point to travel once around the circle. So first off, we're gonna solve this equation for r, just like what we did in the other one. So v equals 2 pi r over t. So since I'm solving for r, the first thing that I'm gonna do is I need to get rid of that t. So I'm gonna multiply both sides by t. So then I'm left with tv equals 2 pi r. And just like we did in the last one, we want to get r by itself, divide both sides by 2 pi. All right, so we're left with that r equals tv over 2 pi. That would be our equation to solve for r. Then it's saying, suppose a merry-go-round is spinning once every 3 seconds. If a point on the outside edge has a speed, which is our v, of 12.56 feet per second, what is the radius? And then it's saying use 3.14 for pi for this problem. Okay, so we're gonna go ahead and plug those numbers into our equation that we just solved for previously. R equals, and then t, remember, is our time, so in this case would be 3 times our velocity, or our speed, 12.56. And then this is gonna all be over 2, and then it says for pi to go ahead and plug in 3.14. So I'm first gonna multiply 3 times 12.56, and I get 37.68. And then if I take 2 times 3.14, 6.28, I'm gonna divide those out. R equals 6, and then this case would be feet. Okay, so that's the first part. Like I said, there's more examples. This is the first part of lesson 2.8. The second part deals with dimensional analysis, and this is where we're bringing in that unit rate, which is what we talked about in lesson 2.6. So when we do dimensional analysis, we're carrying from one unit on, or 1 or 2 units that we might have to change into 1 or 2 different units. So you will definitely need to make sure, like, this conversion chart that's at the bottom here is a great reference. I also have this posted on Canvas as well, so that you can reference to it on your own in case you don't have this chart in front of you. So the first example says a 10K run is 10 kilometers long. If 1 meter is 1.094 yards, use dimensional analysis to find the length of the race in miles. And right there, it gives you a hint that 1 mile is 1,760 yards. That will not always happen, but when it does, take advantage of it. So we first are gonna figure out, all right, we're starting with 10 kilometers. And I'm trying to figure out how long the race is in miles. So what I like to do is write down, where am I starting? Where do I need to finish? So then I can work myself through this problem. So with 10 kilometers, I need to think of unit rates that I can start eliminating other units. So with 10 kilometers, I know that in 1 kilometer, there are 1,000 meters. Okay? And the reason I want to convert kilometers to meters is because in the problem, I'm provided a unit rate that in 1 meter, that's 1.094 yards. So what I will do here is I'm going to cross out the units, just the units, not the number. And now I'm left with meters. I still need to get all the way to miles, so I'm gonna go ahead and multiply this by, and since meters is on the top, I'm gonna put the unit meters on the bottom, and my conversion that I know is that in 1 meter, we have 1 94,000 yards. Meters are gone. I have yards, but I need to get to miles, so that's when this hint comes into play. So remember, I'm gonna move this just so I have space, that in order to get rid of yards, I'm gonna put it on the bottom. And then I know that there are 1,760 yards in 1 mile. Cross out my yards. And since I wanted to get all the way to the length in miles, now I'm done. So what I mean that I'm done is I have converted the kilometers, which is metric, all the way to miles, which is customary. So now I'm gonna go ahead and multiply across like they were they're all fractions. So remember, you multiply across and then multiply across. I'm gonna go ahead and put 10K over 1 just so that I can see my numerators and my denominators. So I'm gonna go ahead and multiply 10 times 1,000 times 1.094, and I end up getting 10,940, yes, divided by 1,760. Now that I'm here, I'm gonna go ahead and divide those out, and I get 6.2 miles. So that would be the conversion of 10 kilometers to miles would be about 6.2 miles. Once again, rounding to the nearest hundredths is probably your best bet, unless it tells you specifically what to round to. All right. On the next one, we'll go ahead and try, let's see, we're gonna go do this first one. So a car travels a distance of 100 feet in about 2.8 seconds. What is the velocity of a car in miles per hour? So our starting point is feet per second, and we're told that we need to get to miles per hour. Notice in this one, we're changing both units. So you wanna focus on changing 1 unit at a time. Okay, so for our feet, we have 100 feet in 2.8 seconds. All right, so I'm gonna go ahead and change my distance first. So to get rid of feet, because I need to get to miles, the only conversion that I know that there are 5,280 feet, and notice how, because feet was originally on the top, I'm putting it on the bottom. There are 5,280 feet in 1 mile. My units only are gonna cancel. And since I got miles now on the numerator like I needed in my answer, I'm gonna circle it, which will indicate that I'm done converting that unit. Now what I gotta do is I gotta get from seconds to hours. So one unit rate that I know is that there are 60 seconds in 1 minute. My seconds units are gone, but I'm at minutes, but I need to get to hours. So in order to get rid of minutes this time, I'm gonna put it on the top. And I know that there are 60 minutes in 1 hour. My minute units are gone. And now I'm left with miles per hour, which is where I need to end up. If you can go from seconds to hours, by all means. What you'll figure out real quickly just looking at this is that there are 3,600 seconds in 1 hour. So if you want to just take it all in one step, feel free to do that. So now that I'm at miles per hour, I'm going to go ahead and multiply my numerator across, which I end up getting 360,000. And then when I multiply 2.8 times 5,280, I get, let's see, what would that be? 2.8 times 5,280. I get 14,784. And then I'm going to go ahead and divide those out. And I get divided by 1 I get 24.35 miles per hour. But notice in this problem, it's asking you around to the nearest whole number. So in this case, your final answer would be 24 miles per hour. Okay. And then let's do, we'll go ahead and do number 2, and then the rest are there for you to try. So the average weight of a chimpanzee at a zoo is 52 kilograms. If 1 gram is about 0.0353 ounces, use dimensional analysis to find the average weight of a chimpanzee in pounds. All right, so for this one, what we need to first start with is we have 52 kilograms, and we need to get all the way to pounds. So notice with this one, there's only 1 unit that we're changing, very similarly to what we were doing on the first example on the other page. So what we have here is our first unit rate that's in our problem is 1 gram. So we have grams to ounces, but we're here with kilogram. So I first need to convert kilograms to grams. So what I know is that in 1 kilogram, kilo means 1,000, that's 1,000 grams. So kilogram units are gone. Now I can use that sentence, that second sentence, and since I know that it's 1 gram, and I had gram on the numerator originally, it's gonna go on the denominator, and then I'm gonna put ounces on the top. And then now I need to get from ounces to pounds. So ounces on the numerator, I'm gonna put it on the bottom. So I know that there are 16 ounces in 1 pound. Ounces, ounces, I'm left with pound. So now I'm gonna go ahead and multiply across. Okay, so I'm gonna do 52 times 1,000 times 0.0353. So 52 times. All right, we get 1,835.6. And then I'm going to multiply across down here, which ends up being just 16. So I'm going to divide that out. And I get 114.725 pounds. All right, that's lesson 2-8.